You are in a class filled with other students, and there is an instructor that teaches you the lecture. This is the instructor, and he teaches many students, 60 students. He's talking, shouting, explaining, and whatever. He will not, or she will not, more likely to count the number of students that are present in the lecture. So what to do is just to pass a certain paper to the students, and then they make each other present. If you, my friend, are absent in one day, and the teacher decided to count the number of students before the class began and after the class finished, they would say the input is 60 students. The output should be 60 students leaving. This would be the ideal case. I have 60 students entering, I have 60 students leaving. But the real case is that the input were about 50 students and the output after the class finished, 25 students. Surprisingly, it means that some of them left the class before it finished. Number of people left, 25 students. Maybe I'm that boring, I didn't explain that perfect. The shocking news is that the attendance paper included 60 people. How is that possible? He or she may ask. From doing this analysis, they discovered that there are some people that make others sign for them to make them attended. Look at us, we are interested and we came to the class prepared and listened throughout the lecture. But input was 50, output was 25. The left one was 25. There is no any student came to the class like new people came, no, 0. And there are no people who withdrew their registration to the course. It should also be 0. Now 50 minus 25 minus 25 plus 0 plus 0 should equal to 0, ensuring that we have the perfect amount that came and gone and left. And this is actually what we call law of mass conservation. You can apply it to anything in the world, whether an engineering discipline, medical discipline, and in chemistry. You can do law of conservation of mass in reactions. The one that we did in high school. You know it. Oxygen plus carbon gives you carbon dioxide. We want to measure now the number of oxygen here. You have 2 and you have 2. You have 1 carbon, you have 1 carbon. This is balancing a chemical reaction. The mass is conserved. You have only one situation where mass may not be conserved, when you have nuclear reaction. But we will never discuss nuclear reaction in fundamentals of chemical engineering, but it's good to read about it. And even I will provide some content about it later on. Now let's talk about the real names of conservation of mass variables. We have input and then we have minus output consumption. If you add it here positive, then this should be negative because it's consumption after all. And then plus generation and then equal to accumulation. So this is the general rule that you will have whenever you solve a problem related to conservation of mass. You will see a lot of things and you will always lead with this equation. And then you cancel the things that are not accounted in the problem you are solving. I did a horrible mistake in the previous page, but I will not come back to it until I illustrate this point now. We have raw materials coming in a process or processes. Could be 1, could be 2, could be many. 1, 2, 3, 4, and then 5. Process unit. This raw material is called the input, and this one is called the output. The input must equal to the output if and only if, math people, we have no accumulation, no leaking. Leaking is like when you have something flowing, escaping the process unit. If there is no generation or consumption, if our measurements are correct. In the previous example, we only had no leaking situation correct, but we had accumulation, we had generation consumption, and we did not do the measurements in a correct way. Now, because we know how to do mass balance or law of conservation of mass, we delete everything and start again. The input should not be 50. If you start with 60 ideally, then the input should be 60. The output, consider that it is 25 students, and the left one, which is in this case the accumulation, you know now what is the meaning of accumulation, is 25 students. And if the generation, the number of people who came in the class, in the middle of the class, is 0, then how to find the consumption? You start with the general equation. Input, which is 60, minus output, which is 25, plus the consumption, which we don't know, we want to find those students who were absent, plus the generation, which is 0. This should equal to accumulation. And we know accumulation is how much? 25. If you solve for consumption, you'll say consumption will equal to 25 plus 25 added to the other side, and it should be negative, minus 60. The answer will be minus 10. In Elementary Principles of Chemical Processes, the book I'm explaining, he wrote in the general mass conservation or material balance rule, he wrote input minus output minus consumption plus generation. And if you put minus consumption, then the answer, you would have it in the end in positive sign. But if you do it like me, plus consumption, then the answer should and must be minus or a negative sign. Because it's consumption, it means you are losing something. It doesn't make sense if you put it here positive, then you have it negative. It doesn't make sense. But you have the option. I prefer that you use minus here, and then the answer should be positive. How to make sure that the solution we did here is correct? Because we did one before, when we put 50, and then we obtained an answer that was logical to us, but it was wrong. Now how to make sure that this equation is correct? If you make the accumulation in the other term with these guys, and then the answer turned out to be 0, then your answer is correct. Let's try it. If you recall, we have 60, input minus 25, output minus consumption, 10, plus generation, 0, and then minus the accumulation, which was 25, the left people. If this is not 0, then you definitely did not make your measurements correct. 60 minus 25 minus 10 minus 25 will actually be 0. Unlike the case we solved before, it was actually minus 10. So it doesn't make sense before. The previous example, we did not face this situation. But we will face it if we have these conditions together. If you have a raw material, and then a process, or many processes, and then you have a product. If this is a physical process, then you will have no generation and no consumption. The only thing you will have is input minus output equal to accumulation. If you have a chemical process, if you recall, at least one chemical reaction makes this a chemical process. In this case, you will have input minus output, as the book wrote, minus consumption plus generation is equal to accumulation. Now, if you have what we call the wonderful word steady state situation. For the physical process, guess what? Input just equal to output. Whatever enters equals whatever leaves. That's simple. But if you have a chemical process, then input minus output minus consumption plus generation will equal to 0. It means that we will not have any accumulation inside the process. We will get rid of this accumulation term, the one that is bothering us, the one that causes us not to have input equal to output in case of physical system. And it would simplify the situation in chemical system. Why I'm ignoring this accumulation and why am I considering steady state? Because most of the chemical plants or physical plants that you will end up working in an industry contain steady state operations. So they do not have accumulation process. They start a process and then they wait and wait and wait and wait for a long duration of time until the process becomes steady state. In that case, if you have a physical process, like the crude oil refining process, then input will equal to output. And if you have a process unit that is chemical, it means we have reaction, then just if you add, subtract, and then consider the consumption, the moles that have been consumed and the moles that have been generated, you will equate this term to 0. But before the process reaches steady state, it was once transient or unsteady state. This will be a term that will be mentioned to you throughout your life as a chemical engineer. Whenever I say transient or unsteady state, you will have this accumulation term, whether you have a physical or a chemical process. And if I didn't say it, if I said that the process is steady state, then say goodbye to the accumulation and it will make your life easy. Now let's have a kind of interesting drug. I'm not going to lie, I see from time to time the number of views that are on my channel. One of them got about 134 views. After seeing the number of views, I forget about it. 1 day, 2 days, and then I come back and then I see it that 2 days later it is still 134 views. The number of views here is independent of time. No matter how days you increase it, 2 days, 3 days, 4, 5, 6, 7, the number of views will be the same. And in that case, we will say that the number of views, no matter how you change it with respect to time, it will be 0. It will never change. It will be always 134 views. 1 day, 2 days, 3 days, 4 days, it will be the same. This is the definition of steady state. And it means that I should have a lot of techniques to increase the number of views as well. So this tells me something. If I see that the number of views is 134, and then I wait 2 days, I came back and then I see it, I hope, 500, then it means that number of views is dependent of time. The more I wait, the more the number of views gets bigger. If you change the number of views with respect to time, the answer will never be 0. It will give me something. This is what we call unsteady state or transient in terms of YouTube and number of views. But now let's discuss the chemical engineering terms. You have a process, the input has a lot of variables. We could have temperature input, pressure input, mass flow rate of the input, T out, P out, the pressure leaving, and the mass flow rate leaving. If this temperature is, for example, 20 degrees Celsius at time equal to 0, after 10 minutes, for example, and I see that the temperature is still 20 degrees Celsius, then this is steady state. If you have T out equal to 40 degrees, and then this is at time maybe equal to 40 minutes. You monitor the stream for about 20 minutes, and then at the 60th minutes, you see that the temperature out is not 40, it's actually 80. It changes with time. This temperature changes with time. Here, temperature does not depend on time. Whether you have it at T equal to 0 minute or T equal to 10 minutes, temperature will be the same. It will be 20. If you want to make it complicated, then at T equal to 0, we'll say P equal to 3 bar. Did I discuss bar? 1 atmosphere is equal to 1.01 bar. Anyway, Pn equal to 3 bar. Mass N is equal to 1100 kilogram per hour. My favorite number. After time equal to 10 minutes, you see that the pressure N is equal to 3 bar. It will be steady. The pressure will be steady. But the mass flow rate N is 1000 kilogram per hour. Maybe there is a leak, I don't know. But it changes with time. So this mass stream will be unsteady rate. It's not all about the stream itself, no. Each variable could be steady state variable or not. If all of them are independent of time, then this whole process is called steady state process. At least one of them. If it is not steady, if it is dependent on time, then the process will not be steady state. I now will give you a good news. All of the problems you will see, and even in your senior design project, you are more likely to solve the problem considering steady state assumption. But some of the courses you will deal with, like process control, mass transfer, they will depend on transient state. A process could be in terms of rate, kilogram per hour, and could be in terms of amount, could be physical, chemical. The physical process and the chemical process could be open system or closed system. When I say open system, then there will be mass transfer. When I say closed, no mass transfer. Energy, in both cases, you will have energy transfer. We can make this one as well here. For closed, no mass transfer. For open, there will be mass transfer. For open and closed, you will have energy transfer. But we have also other names that mean the same thing. When you say open, you are talking about a certain rate flowing with respect to time. This is short for with respect to, relative to. This open is what we call differential balance. It means all of the variables that you will calculate will be a value of rate. Remember the general law of mass conservation: in minus out plus generation minus consumption will equal to accumulation. All of these terms will be a term of rate. Mass in, mass flow rate, minus mass leaving, flow rate, plus the mass. No, we cannot say this. Mole, for example. Mole comes, mole leaves. Then moles generated, but it will be rate. And then mole consumed, all rate, all with a dot, will equal to the mole with respect to the time, accumulation. And it could be closed, which means amount stored in some container. Remember the hand sanitizer example? 80% ethanol, 20% water is an example of a closed container, closed system. Could call it what? Integral balance. Some specific time we started from, and then some specific time we ended at. English prepositions. The example of crude oil coming and then distillation, as we said, it's called fractionating column. And then there will be many products leaving, right? Open system, because there is some rate flowing and there is some rate leaving. We call this one differential. But if you have some container and then you add certain amount, once the process starts, you do not add something here, it will be closed system. We have certain professional names for them. They are 3. We could have batch. This actually describes this one, closed system. Semi-batch. If you add during the process, it will be semi-batch, and then there is nothing leaving here. But if you add and then you start the process and then you didn't add something, it will be batch process. Continuous. Flow rate coming, flow rate leaving, flow rate coming, flow rate leaving, continuously. These are the 3 that you will encounter in any phase and in any process. You will have either batch, semi-batch, or continuous. The continuous is more likely to be steady state. Semi-batch and batch will never, or let's not be excited, will more likely not to be steady state. It will more likely be unsteady state most of the time. They will depend on time. Here it will be actually independent of time. Crude oil leaving and it's purified, and all of the variables that are here are independent of time. So the calculations will be much easier. We will cancel this one, accumulation term. We will make it 0. The amount of the moles or mass with respect to time will be 0. We said a lot of things that are new, but you can relate it easily, step by step. If I said open, then I mean differential, and I mean most likely continuous. If I said or semi-batch, because there is some flowing amount here. If I said closed, then I mean integral, specific time, so there will be amounts, not flow rate, and most likely to be batch and steady state. If you don't get these definitions by now, you will get them later on, definitely, because from this point on, all of the things that will be discussed in material balance will be about solving the problems and then discovering things and then explaining them one by one. But now just an introductory to material balance and the law of conservation of mass, its application not only just in engineering but also in everything you need and everything you think of, and an extension of a process that could be chemical, physical, as we said before, but it also could be open or closed system. If it is open system, we are more likely to talk about rate flowing with respect to time, and if it is closed, we are talking about an amount. An example of each one of them will be discussed in the next video. Or no, wait, before I conclude, I said something before about this equation. I said mass in, mass out, and then I stopped talking about mass. The reason is due to the fact that mass cannot be generated and cannot be consumed. It can only be accumulated. It can enter, it can leave, and it can accumulate in the system. So even if you have a chemical or a physical process, after all, if you are focusing about the total mass, not the mass of a chemical, no, the total mass, then in minus out will equal to accumulation, either if it is chemical or physical. But when you talk about moles, then in minus out will equal to accumulation in terms of mole only for physical process. Total mole will be conserved for physical process, and the total mass will be conserved for chemical and physical process. Another name for physical process is non-reactive system. Makes sense. The one that has no reactions. Chemical, then reactive system. It means we have at least one reaction. And by the way, the same story is applied to energy. Energy cannot be generated nor consumed. Mass cannot be generated nor consumed. They only can change from one form to the other. And actually there is an equation, a famous equation, that relates energy to mass. And that indicates the conversion from mass to energy. And it is this equation. The energy that you want to calculate is equal to m, which is the mass, times c square. This c square is the speed of the light. And this speed of the light is 3 times 10 to the power 8 meter per second. This is called Einstein Equation, but it is not discussed in chemical engineering concepts. But you should know now that there is a conversion between mass and energy. Energy and mass are not generated and are not consumed. They only change from one form to another, and they only enter, leave, and accumulate inside a certain system. We are talking about the total mass and total energy. Now I can put the pin.